welcome to the second session today. This is hands-on fitting and winning probability models using NFL data and R. Luke Stanke is an advanced analytics solution architect with Slalom Consulting, a technology and professional services company in Minneapolis. Luke has expertise in a number of technologies, including R and AWS. He has more than a decade of experience working with sports data, ranging from player level to ticket analytics. Let's give Luke a warm welcome of applause.
Thanks. We were going to do a lot of hands-on, but it's going to be like really hard to code over here, so I quickly took all my code and put it into slide format, so we'll kind of like do side by side what we're doing. But if you want the code that we're working with, I've got it on my Google Drive. Just as an FYI, my in-laws are from Stevens Point, so I was here last night hanging out with them, and apparently they don't have wireless internet, so I couldn't push everything to GitHub kind of right away. So it'll take me a minute just to update everything. Let's see. So yeah, thanks for the introduction. I forgot that was going to be done. I have kind of three areas of expertise. One is advanced analytics. You can think of it as data science. I've got a bunch of 7 years of experience in college of that, and then also more than a decade in the field, working with sports analytics data. I also am an expert in data visualization, and I think that's one of the most important things to do is being able, when you're working with data and you're fitting models and advanced models to the data, how can you explain that to your clients or stakeholders really well? That's kind of like a lost art in terms of when you start really diving into code, how to actually explain it. That's really missed out. And then the third is with cloud services, as mentioned, like AWS. If we're going to scale any of the work that we're doing, so if we're going to be working with streaming or live data, you need to be able to compute really fast, and I have expertise in that area as well. I've been lucky enough to, while working at Slalom and on my own, work in sports for major organizations and smaller organizations, and I've also gotten the opportunity to do ticket analytics for third-party vendors of tickets. Helping them with their analytics and unfortunately trying to outprice you if you're placing your tickets on one of those third-party vendors. So apologies for that, but that's what I got to do, and unfortunately I can't speak to the specific teams I worked with, otherwise that would be a lot more fun to talk about. Anyway, in this session we're going to work with play-by-play data. As I mentioned, ticket analytics are pretty cool, but there is also the area that I think that's biggest emerging is concession analytics and being able to work with that in-game entertainment. That's like the next step for most teams. Of course, sports is entertainment, and with essentially people staying at home and watching games, whether it's football, basketball, or any other sport, how can we can improve that in-game experience with analytics? But like I said, we're going to focus mostly on player level data because it's what's most interesting. Just as an FYI, let's see if I can, if you were going to follow along, you'd be able to get the data from the locations I have up there. So again, it's just written up there. Anyway, what we're going to go through is I'm going to, if you're downloading this, you'll also need to, by the way, install a few packages. Again, I don't see any computers open, so I don't have to worry about this. Here's what we'll be doing in general, how to get the data. I was hoping Ron would go into a little more detail if you were in the first session about how to use NFL Scraper, but either way, like that's the most fun part, and I'm skipping all of that. That's like 99% of the work is actually getting the data. If you're someone who likes to parse through API code or and just general HTML to essentially get the data you need. We'll spend actually a lot more time talking about visualizing the data, doing a little bit of feature engineering, fitting models. I wish I was going to talk in more detail about that, and then getting down to when added results. We're going to cover over 700 lines of code, and I have 90 slides, and from here on out it goes pretty fast. So feel free at the end to ask me any questions if I didn't cover anything in as much detail as you want. So two of the major components that we'll use today are one, the tidyverse. If you've ever used R, this is sort of where you should start. If you're just getting started, this is a set of packages you should use almost immediately and get to learn right away. We're also going to be using Magritter. Magritter takes something like this, so if you're writing code, it looks really ugly, and you have to work from the inside out, so we're going to filter plays by week and type, and then we're going to group things by offense and summarize it. Really hard to see. Magritter is a piping-like package, which allows you to essentially, instead of writing inside out, write left to right, top to bottom. So we're going to take our plays data, we're going to filter it, we're going to group it, and then we're going to summarize that data. So you'll see my code. You can sort of read it like a book if you want, or you can just look at the pretty pictures that go with it. What Ron talked about this morning with points expected, you can take the same sort of approach that we're taking with win probability and apply the same exact theory. It works identically, and what's really nice is if you were here for Ron's talk, is that if you put the two side by side, they provide a much more complete picture of a particular player. And we'll also, while I won't show individual player running backs, Ron talked about running backs is not necessarily adding the amount of value that you would want to or expect from an individual player. And that's generally the same result here. But anyway, we're going to use some AI tools, that's what they call it, but it's really just a distributed platform for doing machine learning called H2o.ai. And we're going to be fitting some win added models. And I don't apologize for having a lot of text there, because I figure if you download these slides, you'll want to know the thing that I said on this slide. So I actually just put it in there for your sake. What are win probability models? They're actually pretty straightforward. It's given a particular play, what is the context, what do they add to winning on that play from one play to the next, or what do they take away? So an example I have on here, which I'm not going to go through in too much depth, but just think of it, if you have the ball and you have the odds on that given play are 34%, and say you throw a pass and you get a first down, and your odds increase to 44% on that given play, it's up 0.1 wins. Or you throw an interception and it goes down to 24%, your odds decrease by 0.1 win odds. So as mentioned, there was a really nice statistician who used to provide this win probability for free, or not necessarily for free, but you could follow along with lots of advanced metrics. And 10 years ago, this was like, man, Brian Burke was really breaking the mold in terms of analytics, and you wish you could get to this kind of information. And how could you ever fit something that's as cool as like win probability, which is now bought by ESPN, or his algorithm was bought by ESPN. But my argument is that every one of us in this room can easily start doing this, and it's not really that hard. What we're going to do today is I'm going to show you how to do that in less, well, I'll show 700 lines of code. You could probably do it in about 50. So why should you use win added models or even point added models? Well, it provides that context of the game on any given play. What are your odds of winning the game? I used to use this like hanging out with friends, as simple as if I was hobbyist, I was hanging out with friends, I'd go to Brian's website and be like, oh yeah, like we can turn off the game. The odds of the comeback are very unlikely. Or even during the Super Bowl this year, I was cooking dinner for my wife and she kept giving me relaying the score. I usually just watch the second half, and she was like, you don't need to watch it. So we kind of turned it off, and then quickly was following on Twitter and had to change our mind in terms of watching it very quickly. But it also can provide player value, and I think that's where the more interesting thing is. Sure, we can directly correlate or directly derive or indirectly derive player value in terms of the wins that they contribute. But we can also start using that as another metric to start comparing maybe prospects coming in, how they compare to other players, and maybe what their value or share of value is going to be in the future. And then I like to use it for play calling strategy, particularly in late game situations. So based on down and distance and time remaining, what sort of play should you be choosing as a coach? And again, what I put together isn't what the answer is. What it is just a recommendation for the stakeholder who may or may not be a coach. It could be somebody else. That's up to the person who's using the data to make the decision. My job is just to provide them with the best information that we have available which is through a number of data sources, including play-by-play.
Forgive me for asking, but in that last slide, did you take out the Washington logo by Kirk Cousins, or was it a third party?
Oh, I don't know.
Okay, just the sociologist knows.
Yeah. So just like a little bit of an overview. So when added models, in this particular situation, it's the fourth quarter. We have 2:15 remaining, you're down 3, 23-26. The ball's on the 30, and it's 2nd and 8. You have about a 47% chance of winning the game. So you're down, but the odds are still there. But if we were to just say, simply change the context of down, so now it's the only thing that changes is 4th and 1, is that odds drop significantly to 39%. Or even if we say like keep everything the same with the exception of 3rd and 10, it's only slightly better. So 4th and 1 versus 3rd and 10 is just a slight difference in terms of win probability. But obviously, as we change the context, like instead of being on your opponent's 30, you're on your own 30, the odds drop even more. Or if we change it to the score is 13-26, so you're down 13, the odds drop even more. Or you have 1:15 left, the odds change even more. So there's lots of different context in play here, and that's really what I'm trying to illustrate here is what you can see in terms of win-added models as we, in this case, approach late game status. So the fun part, which I'm not going to spend a lot of time talking about, but as a you're going to obtain data, there's really 3 ways to do it. One, you can learn how to read through JavaScript, HTML, and extract the data via JSON or use an API to do it. You can, if you're using R, you can use, let's see if this thing works. You can use NFL Scraper, which is an okay package. There are some things that they could do better at in terms of gathering data, or if you're lucky enough, you can just go home and purchase the data, or you can get your client to pay for it, or they have it. So what I did is I have the data available for both games and plays. So this is just some real basic data. What I'm going to do is read it into R, and if we look at the data, just sort of the first 10 rows, we have of games data. This is just every game from 2010 through 2015. We've got week, visitor, home team, points home, the total score for the visitor, the home, and the stadium. I've also got games data, so this is play-by-play data for every game. I have a game ID, a play ID. You can ignore the dseek, that's a variable I created. The offense, the defense, the type of play that was run, the quarter, minute, second. It allows me to give the time during the game, the total points at that given time for the offense, the defense, down distance, where the ball is. That's going to range from 0 to 100. If you are, if you're on the 23, you're on your own 23-yard line. If you're on like the 78, that would be at your opponent's 23-yard line or 22-yard line. Anyway, we also have penalty, time remaining. I actually created the variable already, and yards gained on that play. So this is real typical play-by-play data. You're thinking, what can we do with that in terms of precision? We can actually do a lot. The next step here is I'm going to show you data visualization, and feature engineering was a heavy emphasis on data visualization. Because if you're going to fit models, you need to understand the data before you start fitting models. So what we're going to do is, again, since I designed this for a younger audience, since there are a lot of students here, I put a few slides together on feature engineering, but we don't really need to focus on this. Data visualization, know that it's really important. I already talked about that. So here's some code. Again, if we're looking at the code, I would have showed you via live example. We're going to use P by P, which is a play-by-play data. So what I did is I joined the data together, the game and play data. And then what I did is I took, I wanted the average wins per point differential, regardless of context. And then I just created a line plot and did some cleaning up of it to make it look good. And as you can see, as you score more points, no surprise, you have better odds of winning. That's not super genius material here yet, but that's the point. You want to start with the basics first in terms of the model that you're going to be fitting. Here's the same thing, but the only difference here is time remaining in the game. So if you are in possession of the ball, your odds of winning the game up until the fourth quarter are slightly better than not having the ball. Again, not super genius stuff. And into the fourth quarter, you'll see it drops below 50%. That's because the team that is falling behind is scrambling to try to score points. That's not a surprise. If you've watched football, you know that there's always that hard attempted comeback. here's a really fun plot of point differential and time remaining. So let's start putting those two things into context. And as you can, the green is going to represent the odds of winning are higher, and red is lower, and the yellow is kind of in between. And again, no surprise, when it's a close game, the odds are are less decisive in terms of winning or losing. Again, this plot isn't super interesting, or maybe it is interesting in terms of the color, but it's not really interesting in terms of the information you get from it. So, but all this we're gathering to fit models. We're trying to understand the relationships between variables. And let's just add in a couple other factors, like down. If I have the ball in terms of down, what are the odds and how they change? 0, by the way, represents like a kickoff or extra point, kind of a non-time down. And you can sort of see there's a slight difference between down as game time changes. With fourth quarter, even fourth quarter, early in the game, fourth down is a good sense of there's better odds than if it's first, second, or third down to winning the game when you have it. Very interesting. So the thought process behind that is if you're punting the ball, you're putting the opponent in a worse position for winning the game because they have lower odds in terms of scoring. That's why you'll see that. On fourth down and later in the game, teams are going for more frequently, and you'll see that's why that's decreasing that way. We can also look at, again, this is that point differential by down. This is in a really also very informative plot, but we have all these uninformative plots because we already know this intuition in our head. But as we start putting all these components together, we can start thinking about the interactions within the data and adding them all into a model when we get later down the road. Let's get to some more interesting things. So like down by time of field position. It's fourth down. Again, I'm focused on fourth down for no particular reason other than it deviates from first, second, and third down. Let's go straight to the fun stuff, actually. Play type. Based on play type, so I have a number of different play types. I'm actually going to isolate 2 of them for you. In field position, you'll see that there is this nonlinear relationship, and I'm just going to want to account for that nonlinear relationship in my model. And again, I apologize that I'm going through this really fast, but I have a lot more to cover. And this isn't actually the point of the slides. Anyway, actually I do want to point out one thing, is you'll notice that based on field position, there's these, maybe you can see it, there's these lighter lines behind it. Those are the actual values, and I have these curves kind of just as splines that are fitting through the actual values. That shows that there's a little bit of precision in those splines. But if we take a look at something like field position and play type during the game, you'll see a lot more variability. These splines aren't necessarily as nicely fit. So I have these 2 play type views, and I wanted to focus on play type for a second as a predictor. Because if you think about the models that you're going to be fitting, if you're trying to guess whether you're going to win a game based on the context of a play, you don't actually know what the play type is immediately before it's run. You can only guess to the play before. So I have these play type, and if you're really smart about this, you're like, why am I showing play type? It's to say that I'm doing it wrong. What I actually need to do is look at the previous play. So based on the previous play, what are my odds of winning the game? And these plots generally look the same, but what I wanted to do was focus in on just really passing and rushing. So given all the sort of ignoring all the other contexts, just looking at whether it's a pass or rush for a given play, what are the odds of winning a game? So early on, first 2 quarters of the game, the odds of winning or losing, whether you run or pass, it doesn't matter. But into the third and fourth quarter, particularly into the fourth quarter, when you run the ball, you are more likely to win the game, which is kind of like, we'll get to it. I put this together, and then I was reading, since we're in Wisconsin, and I'm also from Green Bay, and I'm a Packers fan in that sense. I wanted to focus in on, Mike McCarthy's play calling is usually a hot topic on Monday morning, and why is he running the ball out in the fourth quarter, and why does he do that? Because we always the game seems to close in, but this plot would seem to suggest that running the ball, particularly late in the fourth quarter, would be the better option. I mean, when we're looking in the last like 4 minutes of the game, it's almost a 50% difference in winning or losing.
That depends on what the score is at that time.
That's right. You are jumping the gun on where we're going to go with this. This also doesn't take into account any of the context of the game. So that's the big thing. That's actually where we're going to end up. Our very last analysis is going to take a look at that. Here's that lag type play one, and this is now based on field position. So the plots didn't look as nice as what this does. Basically, field position, there's some sort of tiny linear relationship between play type and where you are on the field. So I'm taking all of these variables into account. I'm going to fit a couple of different models, and it'll make sense in a second. What I'm going to do is engineer a few features. Basically, I'm going to create a time remaining variable, and what I'm going to do is bucket that into 15-second segments. This is strictly for regression. If I'm using machine learning, I don't need to do that, but I'm going to do it for regression only. Then I'm going to transform those variables, so I have some polynomials. I'm going to transform the ball, where the ball location is on the field, into polynomials, and the point difference into polynomials. And then I'm going to say, I have a little thing down here that says since punts and field goals get coded as a 0, I'm going to say it's fourth down for those. So if you go deeper into the analysis, some teams kick, if you're thinking about like the end of the first half, some teams kick field goals on first, second, third down. But really the way that data acts is similar to a fourth down field goal kick. And then I have a home field variable, which I created, but I didn't include in my analysis because I didn't want to just include everything in it. And then the last thing I did, which most of you can't see, is I just created that type leg variable and added it into our data. The next thing we're going to do is model our data, and that's really the fun stuff, right? What we're going to do here is we're going to fit GLM. Previous to this, so Ron talked about wanting to go fit mixed models. So I'll usually use a two-step approach with all of these, in addition to using any of these tools. So we'll fit a GLM, which is just going to be, like, I'm not going to go into the stats of it. We'll fit gradient boosting in a deep learning model. And all these are using the general defaults that come with these programs. And if I'm fitting a GLM, I'm taking into account all those plots that I looked at earlier, and I'm just going to input all those variables with lots of interactions that turns out to be like 600 different coefficients. So the power of my model is not the best, but I'm doing my best to minimize variability. One thing I can tell you that I'm not going to do here is I'm not going to use validation on this. I'm just going to fit it just so you can see how a model that does not use cross-validation and then predicted values from it compares to some of the machine learning models where we can do cross-validation. So after I fit my model, what I'm going to do is I'm going to take my play-by-play data, and I'm just going to create a column that's called GLM pred, which represents the predicted values using my model that was play-by-play.glm. And then if you know anything about fitting a generalized linear model, the values that come out of that with a binomial link is it's a logit, so I need to convert that into essentially a probability, so in terms of a percentage. So that's all I'm doing over here. And if I look at one particular game, so I'm going to look at Week 1, 2015 Packers-Bears. It was a Bears home game. So if you think about the model, every time you see the data, it's going to be the odds of the offense winning the game. But if I'm going to create that plot, what that does is it makes it look really not as interesting for a particular, because it's going to constantly waver between the offensive teams. So we're just going to focus on the home team. So this is a plot for the Bears. And you can sort of see the probability as it changes over time for the Bears. Again, this is GLM, just provides a little information. The next thing I'm going to do is I'm going to kick off H2o. I'm going to do some machine learning, some deep learning. And what I'm going to do is I'm going to create a H2o data frame. And that's pretty easy to do. I just essentially select the variables that I want to use from my H2o data frame. And then I have to convert them from characters to factors in order to fit the model. Split the data frame for cross-validation, and then I could take a look at the data. So again, this is This is the not fun stuff, but I wanted to make sure that we cover through every little bit of it so that you can see what 700 lines of code looks like in terms of model overview. So here I'm going to fit simple GBM. There's nothing kind of crazy going on. It's, the tree goes seven layers deep, and I'm fitting 3,000 trees. Again, just using some kind of defaults. I'm also going to fit a more advanced one in terms of fitting. And I can tell you that both of these are okay. And then I'm also going to fit a deep learning model. And I'm going to fit an overfitted deep learning model because what this model does is it doesn't do cross-validation in it. I just wanted to show you what happens when you fit one of these models and really take it to as deep as you can in terms of how much can you actually predict. So what I need to do is then take those values, those predictions out of those models. So I have 3 columns that I'm creating. One for the gradient boosted model, one for that more advanced model, and one for the deep learning model. So what I wanted to do was take those models and let's look at an individual game and how do they compare to each other. Again, this isn't very informative in terms of how great the models are, but it's interesting to see how an individual game can compare fitting 4 different models. Let's see if I have anything else that's interesting in this. Okay. So how good are each of those models? I use a number of fit statistics, but I think the one that we're all statisticians are most familiar with is area under the curve. It's essentially like hit rate. That linear model had 67% accuracy. The first kind of default gradient boosted model had 68% accuracy. The more advanced one is 67.5, and the deep learning is 71.2. Again, context matters in how those fit, so the next thing we'd want to do is not just look at the overall fit, but start considering when do those models actually fit better than each other. So, also other stats you definitely want to use your confusion matrix. If you don't know what this is just a way to look at overall hit rate for those models. And I also like to use AIC for those who are interested. So then we're going to want to start to look at those models in context. So here is model performance based on time remaining in terms of AUC. So you'll see that the deep learning model, remember, is biased for this data, is fitting much better than all those models based on time remaining, so game time. Early on in the game, no surprise, the game kicks off, the odds are 50%. It's because I'm not including home team or some additional context about team ability, are about 50%. Kicking at kickoff. By the end, we can increase that to over 75%. The big surprise here is that even in close games, even in blowouts, these numbers can still remain a little more in parity than we'd want, at least with this basic data. Remember, we're not using anything but box score data. That's it. We're not using additional context. We're not driving out any additional features, like let's look at penalties. Let's look at the number of run plays that we're running, how efficient are our run plays, how efficient are our pass plays. All of those can additionally get added in here to start getting a deeper sense. You can also start looking at overall team ability, a number of different metrics that we can start driving into these models that'll really start to understand how well we can predict a game. So what I wanted to do, again, because we're in Wisconsin and people like the Packers, is let's fit every single win odds game for the Green Bay Packers in 2015. I picked 2015 because there were a couple of fun events that happened that year. A couple of big plays that may have happened. Again, this is the regular season. We've got a bunch of different code. I wanted to show every single one of these models. If it's going up towards 100%, that shows that the Packers were going to win a game. That might be just the home teams who won the game. By the way, the scores are there as well, so you can see whether in week 8 there was a 10. Packers had 10 and Denver had 29, so you can sort of see the odds. Kind of quickly went to a blowout status. There are a couple of closer games like week 10 in Detroit, where it was 18-16, where it was a pretty even game, and then Detroit took over the lead, and then something happened over here. And that also happened over here, which in week 13, we should all be very familiar with, if you're from Wisconsin, would be really familiar with the Rodgers to Rodgers Hail Mary. So just even looking at this, that deep learning model said, oh yeah, the Packers are definitely going to win that in a 61-yard Hail Mary, and that's because of overfitting. So that's not actually the truth, though even the regression model put the Packers in really good odds, again, because it was overfit, but the real odds are about 15% chance that they were going to score and win the game, partly because it was only a 3-point game. So at the time, so there was a good opportunity for the Packers to come back in that game. Another one that's really interesting that we don't talk about that year as much, but there was this game against Detroit in Week 10 that I referenced earlier, and this the box score of it doesn't actually show much that's interesting, like except for this one thing down here when the Packers scored a touchdown. Justin Perillo scored a touchdown with just under 30 seconds remaining, and the score ended up as 18-16, but what happened is the Packers missed out on a 2-point conversion. So if we look at that, like, oh, the odds of the Packers winning are looking pretty good because all they have to do is get this 2-point conversion and then potentially score in overtime. But that obviously didn't happen, so that's where things ended up. Kind of interesting as you start to look at that. But anyway, like, that just looks up win probability overall. What about win added? So as talked about in the last session, here what I'm doing is I'm just going to show you the results of a single game. It's Minnesota versus New Orleans. This is the code that's coming out. And what I want to do is just show the basic math of it. All you're doing is you're going to take the previous value and basically subtract these two values. So here's the previous game. I'm going to convert this value in a second. But this first line of code is just saying take this value, the next value, and put it in the first column. But that runs into some interesting situations because obviously we can subtract those out if it's New Orleans, the New Orleans difference. But what happens when New Orleans gives the ball over to Minnesota? On this particular play, the New Orleans scored a touchdown. So why did their odds drop to 35%? It's because the next play, Minnesota had the ball, so we have to do a quick conversion of that and essentially 1 minus that value. So there's 1 minus that value is now 64%. And if you look at the very end of the data, because we're always grabbing the next value, the very last play of the game is always going to have an NA. How do you fix that? Well, you just put whether a team won or lost based on whether they're on offense, and then you can have the probabilities. And then again, all you need to do is subtract that previous value from the current value, and then you can have win added value for every single game. Again, this is just box score data, real simple stuff to work with. We're not breaking the mold. We're not using internal team data. We're not using third-party data. We're just using some real basic stuff. This is just code to fit every single model over. And then finally, my favorite part, let's visualize the results. So I'm going to use 2014 as an example for a couple of different reasons. Aaron Rodgers won the MVP that year, and again, ESPN came out with QBR. You look at his QBR, it's second to Tony Romo. He actually he had quite a overwhelming win in terms of MVP. He beat out. This is the year that J.J. Watt had a great year and kind of beat out everybody else. And then Tony Romo got 3 MVP votes. So if you're looking at this advanced stat, maybe that matters or maybe it doesn't. Just taking a look, here's what I'm going to do is I just want to look at, let's just start out with the basics. Let's look at offense above expectations. So if we take a look at offense above expectations, here's the top 10 teams. What this is essentially the total win added across each play for every offense. So let's ignore who's on that play. What do those teams go above and beyond? So, but each model sort of provides a different look at it. And my best model, by the way, is just the second column gradient boosted model, and that's what I'm sorting by here. You'll see that Green Bay had pretty good win added, 5.7 wins. That's quite a bit in terms of historical performance. Kind of rivals with the Packers a few years earlier, and also with last year's Atlanta Falcons had a really great values. So let's take a look at just the plots of the different models to sort of get a better perspective of every team. Here's Green Bay in terms of win added, in terms of gradient boosted, and here's that deep learning model. Remember, deep learning is overfitted, but it definitely gives us a sense of what teams are going to look like. Green Bay kind of stands out on one end, Jacksonville on the other, and then a group of teams that are high-performing offensive teams in general. So again, let's go back. We're looking at Rodgers. How does he compare relative to the Packers? I'm going to just plot that out. Rodgers, as you can see, brings about 5.7 wins in terms of win added and 5.5. So he dominates the share of wins for the Packers in particular. Versus Romo is also at 5.5 and 6.3 in these models, so he also dominated the statistics as well. But also Ben Roethlisberger, which if we take a look was probably ignored. He comes in on this list at in 8th place. So he also had a statistically strong year in terms of win added, but he didn't perform in terms of QBR. And the QBR is really should be quite related with the statistics that we're putting out here. Just one more thing, back to running the ball, which we covered earlier, is it was very interesting because I wrote this out, and then after I got done putting my slides together, I went online and I pulled up Acme Packing Company, which is a blog for the Packers, and there's this article that McCarthy's lack of killer instincts is hurting the Packers, and if you've read it today or last night, or it's basically like, why isn't he closing out the games that he should? He should be using his high-powered offense to really finish things off. Again, we'll come back to this plot. This plot didn't take into context. This wasn't a model-based context, but if we do consider the model, so here's me essentially fitting a model that ignores that leg previous play, everything but that previous play, and let's just take a look at that. We have essentially side by side our adjusted and our unadjusted. Again, doesn't take into account the context of the game. What you'll see is that the variability is reduced just slightly in these plots. But let's actually take a look at the context of given the previous play. So if you're behind in a game and you run the ball, your odds actually are better than if you're passing the ball late in the game. If you're down by less than a touchdown, running the ball is better than passing the ball. And if you're up by more than a touchdown, and if by more than a touchdown, I'm using 8 points as the reference here, so including a 2-point conversion. So if you're 9 or more, it doesn't matter what you're doing. You're going to close out this game with an equal probability. So to say that a coach is doing the wrong thing in terms of analytics when running the ball in the fourth quarter, the analytics would point to this, but again, that's using every single player across all the data set, and that might not necessarily take into account an individual team and their ability, at least with this plot. But that's at least giving you a baseline for why you should be running the ball in the fourth quarter, especially late in the game. Just wanted to point out again that what these win-added models can do is provide in-game context. They can provide player value and help with in-game play calling strategy. And I would keep saying particularly late in the fourth quarter, because that's when it's most decisive and you can start to see major differences in win probability. If you're interested, you can reach out to me. I'll be posting these slides. If you're on Twitter, you can follow me, but mostly you don't have to. You can just go and connect with me. I'm going to post my slides and provide a link through that. That's more of what I'm going to do. Any questions? We got quite a bit of time here. Yeah.
When you did the quarterback win added, was that purely just looking at his team and how and the snaps he played, or were you divvying up by?
Yeah. So what you have, the answer to that is, I would normally divvy it up, but for this example, I did not. So the reference earlier in the last session was to use a mixed model, and you should certainly do that. And what that does is that it will parse out the value of a quarterback, a wide receiver, potentially offensive line, the defense that you're up against. And when you have that one-to-one relationship, like Julio Jones only ever receives a pass from Matt Ryan, it's also going to, you can't necessarily split that out as well as what you'd like, but you can use the data from other quarterbacks to drive out and parse those differences. So that's like the next thing that I'm missing in here, and that I could have covered in time, but like I've already just dumped a bunch of information on everybody, is that's the next step you would take in terms of evaluating player performance. And actually, you'd want to start putting it. There's a lot of other context variables that you would want to drive into this in terms of where you're on the field. More about where you're on the field. I have obviously the yardage here, but there's more data out there about what field position looks like. Yeah.
Do you see this being used in real time in the game, like the play selection and such, or is that not there yet?
Yeah, so that actually speaks more to the technology that's available to coaching, and it's not there. So what the best thing that you can do is provide a card for a coach that just provides rear selection, and you have to be really thoughtful about how you're going to put that card together in terms of what decisions they should be making. Potentially in the way that I like to do that, because there's sort of two ways. I can build a grid matrix and start going through that, but that can be a pain. What I like to do is provide a tree, a decision tree. So like, given what down is it, how much time's left, where's the ball, how much are you down, and then based on those trees, be able to say you should go for it or not. That's just sort of
The technology's not there during game time? Is that what you're saying? Or you can't really get to the
on-field
coaches?
technology in terms of coaches being able to make a faster decision. The technology, sure, we can stream that data in hours, but it's not sitting in coaches' hands every day in that game, in the actual game.
Can't have it in the coach's box. I mean, somebody's analyzing it there, and you're kind
I
of
can't
relating
speak
it
to that.
to the offensive coaches.
I can
Okay.
say I can create a play card.
Okay. Thank you.
Yep.
Can you talk a little bit about how you evaluate the accuracy of the win probability model? Because it depends on how long until the end of the game. So how is that evaluation done?
Say that again.
How do you evaluate how accurate these models are?
Yeah. So that's I'm just going to do some real basic cross-validation. Again, these models. What can I say about this? Again, catching me at a. So I can use some general fit statistics. Yes, early on in the game, we should expect that there is a lot of times we're going to be missing in terms of that hit. But there are other ways that we can start to evaluate. For instance, you might want to consider just focusing in on the second half of the game in terms of evaluating models or other key indices. It's really up to you to determine how to choose the best model. Again, context matters, so we might fit multiple models, and given a particular context, we might go with another model, and I think that's what you're probably getting at with it.
But in this analysis here, you were looking at the very end, at the probability given at the very end of the game.
That's
and
right.
If the team win or not.
Yep.
Just at the very end.
Yep.
Okay. So then I would expect earlier to be worse than that, right?
That's right. Yep, that speaks a bit to this plot in terms of being able to hit on wins, be able to predict wins early on. It's not there yet, at least with the data and a box score.
So can you then, because you started 50-50,
Yep.
but you know something about the two teams are playing.
That's right.
Home and home.
Home field advantage, stadium advantage, overall ability of a team, offense, defense, special teams, individual players, are they injured or they're not. You can include all that in these models, and you definitely would want to in order to essentially get a better jump on whether you're going to win the game early on or not. What I wanted to do here was show what you can do at a real basic level with box score data that anybody could do. Yeah, but that's absolutely right. I've cheated and I haven't provided all of the information to you. I've only provided you just a snapshot. Okay, thank you very much.
Thank you. Thank you, Luke.